I'm Rob Tur.
Sam McDonald.
We're from UT Southwestern. We're both EM informaticians. And we're just going to jump into model monitoring for models once they're in production.
I have just one quick question for everybody. How many people are actually have deployed like ML in like and being used in like a production environment?
Cool.
And then I'm guessing other people are in like doing retrospective work only, or kind of in that process. Our system, we're like in the middle of that. We've phased in use of some Epic built ML models in kind of how Brian said that they initially started like in various kind of user groups, and then we're in the process of like trying to cohesively join under like a common governance model and try to develop like an infrastructure for providing. And I think the big issue is like what we're talking about is monitoring. Is it's hard to scale a platform to deliver ML kind of prediction at scale without the capacity to monitor, and then everybody's doing their own monitoring. It doesn't scale nicely.
No disclosures. So we've gone through this whole process today, and you finally find up with a validated model, a validated clinical workflow, a team to actually get it up and running. But what do you do next? So if we go back to Brian's lecture, we're kind of talking about this fourth and fifth stage, right? So not only the governance process for, but the technical aspects of monitoring models that are now out in the real world and accumulating experience over time and making predictions over time. And with Scott's talk with this kind of discussion about quality monitoring, impact assessment, and how do we know that the health of the model itself is still intact, and how do we know that the model is actually doing what it's supposed to be doing? So we're going to be addressing these three questions. The first one we're going to skip through because Brian kind of covered a lot of it and we're short on time. The second is, what is a framework for monitoring production models? And the third is, how do you assess the impact of the model itself? So it's the same group of folks, right? You need your clinical experts, your informaticians, your data scientists, your data engineers, and your EHR analysts. And obviously the graph of these is not just a one-way flow. This is a graph of interaction between all of these groups with regular check-ins over the design, implementation, and deployment process. And I think for basically everybody here, including the attendees, this is no surprise. I think everybody has experience there. But this is much more of a gray zone. And through the search that Sam mostly led, even the big dogs in the field who don't have the weird restraints that we have working in an EHR-based environment, really nobody has fully figured this out. But we're going to kind of lean on the framework laid forth by Eric Breck and the team at Google, who went through their organization and surveyed all of their ML teams to say, how do you guys do this? What do you think the best practices are? And then consolidated those into a testing framework that they use to overlie the entire ML-based testing framework of what they do. And the first thing they do is outline how this is similar and different from a traditional software engineering environment. So in traditional software, you need to do unit testing where each little piece of the software, each component gets tested on its own, and you have a library of testing programs that will check that, both before deployment and afterwards in a retroactive manner. You have integration testing and end-to-end testing that makes sure all the communication between the pieces work. And then you have monitors that look for downtime and system failure. Now, in all of these systems, this obviously still applies, but now you have a whole bunch of different tests on the data itself, and whether the data in the validation environment and the testing environment actually matches the data in the serving or production environment. You have skewed testing about whether the model subsequently still behaves once you go even from a validation environment using production data for reasons that we'll outline. And then you get into the actual data monitoring of the things that are coming through, whether they are remaining within the bounds that you expect of those data, whether the monitoring is predicting within the bounds that you expect for the model itself. And you can imagine this gets pretty complex, especially for systems that are inherently not always the most discoverable. But they list, for each of those steps, a framework that you can use. And so we're just going to leave these papers. These are the papers we're going to reference. If anybody wants to just snap a picture at the end of the talk so you can look this up in more detail, especially because we're going to kind of buzz through these. But the 7 components are basically dependency changes result in notification, data invariants hold for inputs, training and serving are not skewed, models are not too stale, Models are numerically stable, computing performance has not regressed, and prediction quality has not regressed. So we're going to zip through these briefly, and then I'll pass it over to Sandy, who's going to talk about some applications of this in our kind of strange healthcare environment. So dependency changes is referring to the fact that most of these systems depend not just on the EHR and not on the model system, but from a bunch of upstream information systems. And you need to regularly monitor that those are working. And that doesn't just mean technically monitor that those are working. That means building the relationships with those teams and the communication channels with those teams to proactively know, in our environment, it might be at Novanote season, right? Everybody gets together and they examine whether or not something that's going to change in somebody else's system is going to have a downstream effect on your data. This is an example from our institution where there was a sudden spike with patients having a different threshold without any other known thing. And Sam was there. I hadn't actually shown up yet, but if you would have briefly
this was my fault. And basically, I didn't pull the data from prior, but we transitioned lab information systems from Sunquest to Beaker in right at the beginning, right 2018-12 or so. And our prediction, basically our prediction output dropped the scores down to a low base level, and then we weren't monitoring this. This is kind of a big goof from our aspect, and we found out that the component IDs changed for the labs when we transitioned to Epic Beaker, and so once we updated those, all of a sudden our prediction scores are bouncing to higher scores. They're distributed fairly similarly, so you see that the input from everybody's getting, probably looks like a lot of people are getting these scores, but they weren't appropriately scored. So this is definitely a dependency issue on other information systems when you're using ML in production.
So a data invariant is sort of a data elements definition. It's what makes that data the thing that it is. And so this may be numerical bounds for numerical data. So age has to be within a reasonable limit, or height, or some other clinical piece of data. And this is making sure that not only when you define a model, but also that the production environment explicitly and proactively checks to make sure that the data coming in meets the same expectations that you had when you built the model. Training and serving are not skewed. And what this means is that you might have different ways that data elements, that the individual factors are calculated. For instance, if you're dealing with user interface inputs, those aren't going to exist in your training and validation environment, but they will in your serving environment, and you need to think about how that's going to work. In our environment, you can imagine lab data being calculated in one place and coming in from somewhere else, and if you're not paying attention to how that happens, either data representation can change on the fly in your serving environment, or the actual values can be different.
And then kind of alluding back to our data talks earlier, depending on where you get your data and what data is available to train on and what data is available actually in production at the time you're trying to deliver the predictions can be discordant and develop that skew. So you may not get the same prediction you would get with your training data.
This is one that the Google folks really, really, really emphasize, which is not allowing your models to get stale. And they actually mean this in two ways. So the one that I think we all think about is the actual age of the model and the fact that there's going to be data drift and changes in the inputs that will accordingly change the calibration of the model. But the bigger thing that they brought up when they interviewed the teams is it's not that, it's a personnel thing, it's a teams thing, and if you're not regularly validating it, you lose the memory of how to actually get that model tested, run through all of your regression testing, and get it back into the production environment. And so really, it's not just about the model, but it's about keeping your team rehearsed on how to keep this thing updated and moving through your system. So this is talking about the outputs, the fact that most systems won't detect issues when you wind up getting outputs that are either not a number or infinite values, because they're not really getting calculated on anything. And often they fit within the data type that you're using. And so this is another thing that they said most teams don't explicitly test for, and it's an issue. Computing performance has not regressed. For them, it's more about computation because they're using much more complex models. For us, it's probably more about the impact that we have on the EHR, so we flip that one around. And that prediction quality has not regressed. And this is obviously challenging because most of the time in clinical medicine, we can't immediately label the outcomes that we have without going back and doing it explicitly. And they talk a lot about how you can do that, and that's in the paper, so I recommend you get to that just so that we can keep moving. bottom line is it's pretty easy to check uptime. You're going to know when the model breaks completely, but there's a lot of little pieces that may be going on underneath. And if you do this type of proactive testing framework, it can really help you from running into issues. So I'm going to pass it to Sam for some impact discussion and some examples of this.
I think those first part is the most important stuff to deliver about monitoring, because the things we don't really think about, all we think about is like, oh, let's see how good our predictions are, and then maybe we go back, retrain our model, and then reassess our predictions. All those other steps actually make it to where your assessment of the output of your model is completely invalid, because all these other expectations that you're assuming were right are basically wrong. And so this is pretty straightforward for kind of clinicians or researchers. Like, how do you assess the impact out of like a predictive model that you know is accurately predicting and the data that's going into it is appropriate? And so it's like, does it provide your measures of kind of statistics that you're interested in appropriately? You know, maybe there's been some drift in the population, like, oh, we need to go retrain and kind of do all these steps. So there's an impact measure there. And then for the CDS people, or the people that have to worry about the CDS, it's like, what's your prediction frequency and when are you providing that prediction? You know, maybe the data that you once had is gone now at the time you're delivering those predictions, and you have to realize that maybe you move when the predictions are delivered, or another type of, like, maybe it's like a pull or push request for the prediction. And then your adherence rates, like maybe you're giving a good prediction, but like it's a dumb moment, right? It's like someone's already started, you know, they say, hey, this person's at high risk for sepsis. And you're like, yeah, I actually gave them antibiotics 2 hours ago, and they have admission to the ICU already, kind of thing. And the kind of thing is like, we talk about prediction all the time, but we never talk about decision optimization. It's like, yeah, we have a prediction, but the next step is like, are there any decisions left to make on this patient? And so I think that's really the future of like scaling AI in healthcare, is that, well, yeah, we have a patient at risk for something, but like, what decisions are left to make, and are there any interventions left? And there's always probably something you can do, but like I think we need that next step to make people really adopt some of this work. And then cost, risk, benefit balance. We talk about risk benefit all the time, but then there's cost too in production and utilizing models. You know, if you're using Epic stuff, you get like in their cognitive computing, you get cost per model after a certain point, and cost of use for every prediction. So some of these things, if you're kind of in this situation, you can't just blindly open up every model and run it, you know, batch run it every 5 minutes kind of thing. And then we have a few examples. This is just some dumb moments from us. We deployed the sepsis model, and then I hit my in basket, and it's like service desk request, complaint about the CDS, complaint about the CDS, complaint about the CDS, complaint about the CDS. Like 2 days in, it's like 20 emails, and you're just like, okay, well, let me look at our awesome Power BI dashboard about our CDS. And if you can't see, basically all the colors, none of the colors on there other than the sliver of orange right here and right here are follow-up action from our CDS taken, right? So like, we were so stoked about it, like, we did all this back testing. Our predictive value for this was reasonably good. It was better than our service model that we're using, so we're like, okay, this is gonna be better. And it was complete garbage, right? So it's like, it's these little things where you need to have a constant, frequent monitor, and don't let this run and then go check, so that you know when you're drifting or when it's not appropriate. And then this is kind of a transition, is Duke put out a paper on like how they're monitoring using one of Epic's models. And I thought they had a nice kind of mental model for how to do this for a single model. And then like, I think the next step is scaling this out. So they showed that they used the Epic model. And what they did really nicely is one of these tests is they actually subdivided the different populations the model is being applied to, and actually assessed their measures of accuracy on these individual populations. And this is one key feature we'll get to that avoids some of these risks of fairness and bias in model, is when you look at subpopulations and apply that model and make sure that your output and your prediction, your predictivity of it is appropriate for each population.
You just mentioned before we were talking, because one thing we really didn't get into is they really emphasize the importance on all of those tests to not just do it for the whole population, but to do it for the same slices.
Yeah, slice it down so you know there's not like some hidden bias or confounding in there. And here they like monitor their actual outcome, right? Their daily readmission rate, to make sure that there's not a prevalence change, so that their accuracy statistics that they're using are still appropriate. Like using your predictive values that's reliant on your prevalence. And so like kind of knowing what your outcome is, make sure that you know that the prediction model that you have is appropriate for that time. And here's nice is that they actually just measured the output of their model too over time. So make sure they're not having any of those misses like we had, where all of a sudden our model score is changing and the model is not functioning appropriately. and it's potentially a test on that dependency, like we talked about in check 1. And then this is kind of nice too, is they actually model for they've modeled for the actual adherence to the recommendation from the prediction model. So you can see your users are actually using it. So on the top is red is like a high score. Your high score actually has like an intervention applied, and the low score is basically the no intervention applied. And those bounds are really nice and tight, meaning that there's not a lot of people with low scores getting this intervention. You can only this is good only when that model is good and is really identifying the patient appropriately. And this is the big one, right? And I wish we had like more time to talk about this. But this is the ProPublica. People know what this article was. It was like 2016, ProPublica. Basically, it was the first kind of eye-opener that there can be like bias and unfairness in actually operationalized models. And what were we seeing is that we were seeing that, you see it right here actually. So we say that Black African Americans were actually labeled at higher risk, but had a less likely chance of reoffending in the same cohort as the whites. And this is operationalized and being used in practice as a huge eye-opener for people. Has actually spurred a lot of like really great work on ethical use of ML, appropriate fairness, and is working on establishing a set of rules and criteria to actually make sure this doesn't happen. This is so important in healthcare too, when we have varying populations that we're caring for, and we're trying to use one model for all, right? So there's a couple good papers here that have been done at looking at fairness in ML and like there's some kind of common constraints that we need to use. And this one I liked a lot, is it kind of gave like an ethical approach to development models, starting from your choice of data, inclusion of the right populations in the choice of that data and the development of this model, and then appropriate monitoring. And a big thing here is kind of slicing down the populations so that each population you're assessing the predictivity on that model, and also ensuring that the data used in that model has the appropriate populations initially, right? So this goes back to that first picture, is like we have a data issue, we have a model issue, and then we have a system issue, and each one of those things you need to assess for any bias there. Cool. Hopefully we didn't go too slowly. Any questions?